How big is too big to understand? Tonight, we're going to explore the true scale of our universe and discover why Earth might as well not exist at all. You've probably heard that the universe is big. You've seen those comparisons of Earth to the Sun or our solar system to nearby stars. But here's what most people don't realize. Those comparisons don't even begin to scratch the surface of how vast space truly is. By the end of this journey, you're going to understand exactly why finding Earth in the universe is like finding a single atom in all the world's oceans. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. Right now, as you sit or stand wherever you are, the ground beneath your feet feels solid, permanent, vast. Earth seems enormous when you walk through its streets, occupying the entire visible horizon around you. The pavement stretches endlessly in every direction you can see. Buildings tower above, mountains rise in the distance, oceans extend beyond sight. This is your world, and it feels infinite. But let me share something with you that might shift how you see everything around you right now. You, as an adult human, measure roughly 1.7 meters tall. The Earth beneath your feet has a diameter of 12,756 kilometers at the equator. That means Earth is approximately 7.5 million times larger than you in height. Think about that for a moment. 7.5 million times larger. It's a number so vast that your mind struggles to grasp its true meaning. To put this in perspective, if Earth were shrunk down to the size of a basketball, you would be smaller than a grain of dust invisible to the naked eye. You wouldn't just be tiny. You would be completely undetectable, lost in the microscopic texture of the ball's surface. Even with a magnifying glass, you would remain invisible, a speck so small it defies perception. And yet, here's what's remarkable. Every single event in human history, every war that shaped nations, every empire that rose and fell, every scientific discovery that changed our understanding of reality, every love story, every tragedy, every moment of triumph, all of it happened on this surface that seems limitless to us. The entire surface area of our planet spans approximately 510 million square kilometers, including both the vast oceans and all the continents combined. Try to imagine that number, 510 million square kilometers. If you decided to walk around Earth's equator without stopping, maintaining a steady pace of 4 kilometers per hour, you would need to walk continuously for 4 years. 4 entire years of walking, day and night, without rest, just to trace one circle around this sphere we call home. During those 4 years of walking, you would cross continents, wade through rivers, traverse deserts, climb mountains, and somehow cross vast oceans. You would experience every climate zone, witness countless sunrises and sunsets, and still be walking on the same small planet. The journey itself would span the entire undergraduate college experience, or a full presidential term, just to circle once around what feels like our infinite world. The oceans alone cover 361 million square kilometers. That's about 71% of our planet's total surface. Imagine trying to comprehend that much water. These oceans create an underwater world far larger than all the continents combined, a realm mostly unexplored and mysterious. We know more about the surface of Mars than we do about the deepest parts of our own planet's oceans. The average depth of these oceans is 3,688 meters. If you could somehow walk straight down into the sea from the surface, it would take you over an hour of continuous downward walking just to reach the average ocean floor. And that's just the average. In many places, the depths plunge much, much deeper. Consider Mount Everest, the highest point on our planet, stretching 8,849 meters above sea level. It seems like an imposing, massive peak when you see photographs of climbers struggling to reach its summit, their faces hidden behind oxygen masks, their bodies pushed to the absolute limits of human endurance. But here's something that puts it in perspective. If Earth were perfectly smooth, like a polished billiard ball, Everest would be nothing more than a microscopic irregularity on the surface, barely detectable even under close examination. You could run your finger across this theoretical smooth Earth and never feel Everest at all. In the deepest place we've discovered on our planet, the Mariana Trench, the seafloor plunges down 10,994 meters below the surface. That's deeper than Everest is tall. If you could somehow place Mount Everest in the deepest part of the Mariana Trench, the peak would still be over 2,000 meters underwater. Yet even this colossal depth, this seemingly impossible chasm that represents the extreme limits of our planet's geography, represents less than 0.1% of Earth's radius measured from the center. The center of our planet lies 6,371 kilometers below your feet right now. That's a distance impossible to drill with any technology we currently possess. We've never come even close to reaching Earth's core. The deepest we've ever drilled is about 12 kilometers down. And that project, the Soviet Union's Kola Super Deep Borehole, took decades to complete and pushed drilling technology to its absolute limits. 12 kilometers sounds impressive until you realize it's not even scratching the surface in terms of reaching the center. It's like poking a needle 1 millimeter into a basketball. Here's something that might make you pause and reconsider the very nature of matter itself. If we could somehow remove all the empty space between atoms, the vast emptiness that exists within every piece of matter, the spaces between electrons and nuclei that make up 99.9999% of every atom, the entire Earth would shrink down to fit inside a large building. All of this solid ground you're standing on, all the mountains and oceans, all the rock and metal and water, compressed into something roughly the size of a city block. This reveals something profound about the nature of reality itself. What feels solid beneath your feet is mostly empty space. The atoms that make up the ground, the chair you're sitting on, even your own body, are like tiny solar systems with enormous gaps between the particles. We live in a world that is fundamentally more space than substance. Right now, approximately 7.9 billion people live on this planet, each person believing they occupy a meaningful space in the world around them. And in human terms, that's absolutely true. But all our cities, all our farmlands, all our forests, everything humanity has ever built or touched, occupies only a paper-thin layer on the surface of this rocky sphere. If Earth's 5 billion-year history were compressed into a single day, human civilization would appear in the last few seconds before midnight. All the great civilizations of history, Egypt with its pyramids, Rome with its empire spanning continents, China with its 1,000-year dynasties, all of human art, literature, music, and scientific achievement exists in a layer so thin it would be invisible if you looked at Earth from space with the naked eye. Above your head right now, Earth's atmosphere extends upward about 100 kilometers, forming a protective film around our planet. If Earth were the size of an apple, this entire atmosphere, everything that allows you to breathe, all the air that contains our weather and protects us from the vacuum of space, would be thinner than the apple's skin. Think about that comparison for a moment. An apple's skin is, a few hundredths of a millimeter thick? That's how thin our protective atmospheric layer is relative to our planet. Everything that makes life possible, all the air that fills your lungs right now, exists in this impossibly delicate shell around our world. Commercial airliners cruise at about 10 kilometers altitude, still well within the troposphere where all our weather occurs, At that height, you're barely beginning to leave the thickest part of our atmospheric blanket. Passengers looking out airplane windows are seeing Earth from what amounts to the very bottom edge of space. Yet the planet still appears to stretch endlessly in all directions. The International Space Station, orbiting at 408 kilometers above, seems incredibly far away when you look up at it passing overhead as a bright dot in the night sky. Yet that distance is still minuscule compared to the size of the planet itself. It's like hovering just barely above the surface of that basketball we imagined earlier. From the space station's altitude, astronauts can see roughly 3,000 kilometers of Earth's surface stretching in all directions. They describe the view as breathtaking, overwhelming, a perspective that fundamentally changes how they see our world. Yet even from this vantage point, they're seeing only a small fraction of Earth's total surface. The curvature of our world only becomes clearly visible once you rise above 10 kilometers. Below that altitude, Earth still appears flat, extending endlessly to the horizon, maintaining the illusion of infinite size. Geostationary satellites orbit much higher, 35,186 kilometers above the equator. That's about 2.8 times Earth's diameter away from the center. At this distance, they take exactly 24 hours to complete one orbit, staying fixed above the same spot on the planet's surface. This synchronized dance allows them to provide consistent communication coverage, but it also represents our first real step away from Earth's immediate vicinity. But even these satellites pale in comparison to our nearest celestial neighbor. The Moon orbits at an average distance of 384,400 kilometers, roughly 30 times Earth's diameter. If Earth were a basketball sitting on a table, the Moon would be a tennis ball orbiting 7 meters away. This distance to the Moon seems vast from our human perspective, doesn't it? It took the Apollo astronauts 3 days of continuous travel at tremendous speeds to cross this gap. Yet it represents merely the first tentative step away from our home world. Light, traveling at its incredible speed of 300,000 kilometers per second, takes only 1.3 seconds to journey from Earth to the Moon, just over 1 second for light to cross what feels like an enormous gulf to us. When you look up at the Moon in the night sky, you're seeing light that left its surface just over a second ago. In the time it takes you to say hello, light could travel from Earth to the Moon and back. This helps put our cosmic neighborhood in perspective. What seems impossibly distant to us is actually remarkably close in the grand scheme of space. Everything you know as reality, your relationships, your ambitions, your fears, your dreams, the daily concerns that occupy your thoughts, the news that shapes your understanding of current events, the problems that keep you awake at night. All of this happens on this sphere that we're about to discover is infinitesimally small. This world that feels so vast and permanent beneath your feet is actually just the beginning of a journey into scales that will challenge everything you think you understand about size, distance, and significance. The illusion of Earth's enormity is so complete, so convincing, that it takes a conscious effort to step back and see it for what it truly is. A tiny island of matter in an ocean of space so vast that our minds struggle to even begin comprehending its true scale. And we haven't even begun to venture beyond our immediate cosmic neighborhood. But to truly understand how small Earth is, we need to step back and look at the family of worlds we belong to, our solar system. At the center of everything we call home sits an object so massive it defies comprehension. The Sun contains 99.86% of all the mass in our entire solar system. Everything else, all the planets, moons, asteroids, comets, dust, and gas, represents just 14% of the total. The Sun gravitationally dominates everything around it for billions of kilometers in every direction. To put this in perspective, if Earth were a grain of black pepper sitting on a table, the Sun would be a basketball with a 28-centimeter diameter sitting next to it. You could hold that basketball in your arms, but the grain of pepper would be almost invisible unless you looked carefully. The Sun's diameter measures approximately 1.39 million kilometers. That's about 109 times the diameter of Earth. Try to visualize this. If you lined up 109 Earths in a row, touching edge to edge, they would just span the width of the Sun. But that's thinking in just one dimension. When you consider volume, the numbers become even more staggering. You could fit approximately 1.3 million Earths inside the Sun. 1.3 million with room to spare between them. Imagine trying to count that many objects. If you counted one Earth-sized sphere every second, it would take you over 2 weeks of continuous counting, day and night, to reach 1.3 million. The mass of the Sun is even more overwhelming than its size. It weighs about 333,000 times more than Earth. If you could somehow place the Sun on one side of a cosmic balance scale, you would need to pile 333,000 Earths on the other side just to make it level. 333,000 of our entire world wouldn't even tip the scales. Earth orbits this massive star at an average distance of 150 million kilometers. This distance is so fundamental to astronomy that it has its own name, 1 astronomical unit, or AU. It's our cosmic measuring stick, our standard for understanding distances within our solar family. The light warming your face right now, the sunlight streaming through your window, or the glow that lit your way today, began its journey 8 minutes and 20 seconds ago. It traveled 150 million kilometers through the vacuum of space at the speed of light, 300,000 kilometers per second, just to reach you. If the Sun suddenly vanished at this very moment, you would continue to see it shining in the sky for another 8 minutes before Earth plunged into eternal darkness. Think about that for a moment. The Sun you see is always the Sun from 8 minutes ago. You're constantly looking into the past, seeing our star not as it is, but as it was when the light began its journey to your eyes. Mercury, the innermost planet, orbits much closer to our star, just 58 million kilometers away. At that distance, it receives sunlight so intense that surface temperatures reach over 400 degrees Celsius. Mercury's year lasts only 88 Earth days. It races around the Sun in the time it takes us to experience less than 3 months. Venus, often called Earth's twin because of its similar size, orbits at 108 million kilometers from the Sun. Its diameter measures 12,104 kilometers, just 600 kilometers smaller than Earth. Yet, despite this similarity in size, Venus is a hellscape of crushing atmospheric pressure and temperatures hot enough to melt lead. The greenhouse effect gone catastrophically wrong. Mars, the red planet that captures our imagination and hosts our robotic explorers, lies 228 million kilometers from the Sun. That's about 1.5 times our distance. Mars has roughly half Earth's diameter, making it a smaller, colder world where a day lasts about 24 hours and 37 minutes, remarkably similar to our own. Yet the similarities end there. Mars is a frozen desert with an atmosphere so thin you couldn't breathe it, and temperatures that plunge far below anything Earth experiences. But these inner planets are dwarfed by the giants that orbit in the outer reaches of our system. Jupiter is truly colossal. With a diameter of 142,984 kilometers, it's about 11 times wider than Earth. If Jupiter were a hollow sphere, you could pack more than 1,300 Earths inside it, with room for them to move around freely. Imagine 1,300 versions of our entire world, with all their continents and oceans floating around inside Jupiter's vast interior. Jupiter orbits the Sun at a distance of 778 million kilometers, more than 5 times farther than Earth. At that distance, sunlight is 25 times weaker than what we receive. The Sun appears as just a bright star in Jupiter's sky, providing little warmth to this gas giant whose powerful magnetic field and swirling storms dwarf anything on our planet. Saturn, with its magnificent rings that have fascinated astronomers for centuries, orbits even farther out. 1.4 billion kilometers from the Sun, that's almost 10 times Earth's distance. Saturn's diameter reaches 536 kilometers, making it about 9 times wider than Earth. Despite its enormous size, Saturn is so light for its volume that it would actually float if you could find an ocean large enough to hold it. The outer edge of our planetary family stretches even farther. Uranus orbits at 2.9 billion kilometers from the Sun, while Neptune, the most distant major planet, lies at an impressive 4.5 billion kilometers away. Neptune is so far from the Sun that it takes 165 Earth years to complete just one orbit. When Neptune was discovered in 1846, it has completed less than one full trip around the Sun even now. But our solar system doesn't end with Neptune. Beyond the orbit of the outermost planet lies the Kuiper Belt, a region filled with icy bodies and dwarf planets that extends to about 50 astronomical units from the Sun. Pluto, once considered our 9th planet, but now classified as a dwarf planet, follows an elliptical orbit that takes it between 30 and 49 AU from the Sun. At its farthest point, Pluto receives sunlight 1,000 times weaker than Earth does. Even farther out lies the Oort cloud, a spherical shell of frozen comets that surrounds our entire solar system. This cloud extends to approximately 100,000 astronomical units from the Sun. That's roughly 1.87 light-years away. To put that in perspective, it would take light, traveling at its ultimate cosmic speed limit, almost 2 years to reach the outer edge of the Oort cloud from the Sun. A light year represents the distance light travels in one complete year, approximately 9.46 trillion kilometers. It's a number so large that it becomes almost meaningless in human terms. If you could drive a car at highway speeds without stopping, it would take you over 10 million years to travel just 1 light year. The Voyager 1 spacecraft launched in 1977 and traveling at an impressive 61,000 kilometers per hour, as it heads away from the Sun, represents humanity's most distant emissary. Even at this incredible speed, faster than anything humans have ever built, Voyager would need 73,000 years to reach the nearest star beyond our Sun. 73,000 years, that's longer than all of recorded human history. Currently, Voyager 1 has traveled about 24 billion kilometers from Earth, making it the most distant human-made object in existence. This distance seems astronomical from our perspective, and it represents an incredible achievement of human engineering and ambition. Yet it equals only 0.02 light-years, 2/1000ths of a light-year, a microscopic fraction of the distance to even our nearest stellar neighbor. To help visualize the true scale we're dealing with, if our entire solar system were shrunk down to the size of a coin lying on a table, the nearest star would be located 300 meters away, 3 football fields distant. Our solar system, vast as it seems, would fit in your pocket, while the next closest star system would be across the street, down the block, and around several corners. We're beginning to realize that even our immediate cosmic neighborhood, this solar system that seems so vast it takes spacecraft decades to cross, is dominated by distances that dwarf human comprehension and vast emptiness between objects. The spaces between worlds are so immense that they make the spaces within our world seem infinitesimal. Earth, already tiny compared to the Sun, becomes even more insignificant when we consider it against the backdrop of our solar system's true dimensions. And yet, our solar system itself is just a tiny speck in something far, far larger. Something that will make even these vast interplanetary distances seem like mere steps across a room. The nearest star to our Sun is Proxima Centauri, located 4.24 light-years away from our solar system. That distance equals approximately 40 trillion kilometers. 40 trillion. It's a number that transcends any earthly experience you've ever had. To put this in human terms, if you could travel at 100,000 kilometers per hour without stopping, faster than any spacecraft we've ever built, it would take you more than 45,000 years to reach our nearest stellar neighbor. 45,000 years. That's longer than all of recorded human history. When our ancestors were painting on cave walls, you could have started that journey and still be traveling today, not even halfway to your destination. Every generation of your family tree from the dawn of civilization to now could live and die during that single voyage to the closest star. Proxima Centauri itself is a humble star, a red dwarf with only 14% of our sun's mass and far less luminous. If you could somehow transport yourself there and look back toward our solar system, our sun would appear as nothing more than a moderately bright star in an alien constellation. From that perspective, Earth would be completely invisible, lost in the sun's glare, undetectable even with the most powerful telescopes imaginable. Within a radius of 16.3 light-years around our sun, astronomers have cataloged approximately 53 star systems. This represents our immediate stellar neighborhood, our cosmic suburb, if you will, and within this entire neighborhood, we've confirmed the existence of only 8 planets orbiting other stars, 8 worlds in a region of space containing dozens of stellar systems. This sparse distribution gives you a sense of how rare planetary systems might be, or perhaps how difficult they are to detect across such vast distances. Most of the stars in our neighborhood appear to be solitary, burning alone in the darkness, without the planetary families that make our sun special. These 53 nearby star systems are part of something much, much larger. The Milky Way galaxy is a spiral galaxy containing between 100 billion and 400 billion stars, each one burning independently in the cosmic dark. Estimating the exact number is impossible. The galaxy is simply too vast, and many stars too dim to count. But 200 billion serves as a reasonable approximation based on our best astronomical observations. 200 billion stars. If you could count 1 star per second without pause, working continuously day and night, it would take you approximately 6,300 years to count them all. 63 centuries of counting just to catalog the members of our galactic home. You could start counting when the pyramids were built and still be counting today. The Milky Way stretches about 100,000 light-years from edge to edge. Remember, light takes 4.24 years just to reach our nearest stellar neighbor. Now imagine that distance multiplied by 25,000. That's the span of our galaxy. The galactic disk has a thickness of roughly 1,000 light-years in the spiral arm regions where young hot stars are born and live their relatively brief but brilliant lives. At the center of our galaxy lies a dense bulge about 10,000 light-years in diameter, packed with ancient stars that formed when the universe was young. These are the galactic elders, red and orange giants that have witnessed billions of years of cosmic history. And at the very heart of this central bulge lurks something even more extraordinary. A supermassive black hole with the mass of 4 million suns. Our sun sits approximately 27,000 light-years from this galactic center. We're located in the galactic suburbs, far from the crowded energetic core, where stars are packed much more densely than in our peaceful neighborhood. We reside in what astronomers call the Orion Arm, a relatively minor spiral structure wedged between the larger Perseus and Sagittarius Carina arms of the galaxy. The entire solar system, our sun, Earth, all the planets, everything we've ever known. orbits around the galactic center at a speed of 230 kilometers per second. That's over 800,000 kilometers per hour. We're racing through space faster than you can imagine, yet the galaxy is so vast that even at this tremendous velocity, it takes us approximately 250 million years to complete one full orbit around the galactic center. Since Earth formed 4.5 billion years ago, our solar system has completed only about 18 trips around the galaxy. 18 orbits in the entire history of our planet. When the dinosaurs walked the Earth 100 million years ago, our solar system was in a completely different part of the galaxy. The star patterns visible in Earth's sky, the cosmic radiation environment, even our proximity to spiral arms where new stars are born, everything was different. To truly grasp the scale we're dealing with, if the Milky Way were shrunk down to the size of a football field, our entire solar system would be smaller than a grain of mustard seed placed somewhere near the 30-yard line. And within that mustard seed, Earth would be completely invisible, even with the most powerful microscopes available today. Think about that for a moment. In a football field representing our galaxy, you couldn't find Earth even if you knew exactly where to look. It would be lost in the texture of a mustard seed, billions of times smaller than anything you could possibly detect. The Milky Way contains not just stars, but an estimated 100 billion planets scattered throughout its spiral arms. Current statistical analysis suggests that approximately 20% of Sun-like stars possess planets within their habitable zones, regions where liquid water could exist on planetary surfaces. This means there could be billions of potentially habitable worlds within our galaxy alone. Yet the nearest star with a confirmed planet in the habitable zone might be hundreds of light years away, even if we could build spacecraft capable of traveling at 10% the speed of light, a technological achievement far beyond our current capabilities. Such a journey would take thousands of years. The travelers who arrived would be the distant descendants of those who departed, carrying forward a mission begun by ancestors they never knew. Our galaxy also contains vast stellar nurseries, nebulae where new stars are constantly being born from the gravitational collapse of gas and dust clouds. The Orion Nebula, visible to your naked eye as a fuzzy star in the constellation Orion, lies 1,144 light-years away and spans 24 light-years in diameter. Within this single cloud, thousands of new stars are forming, each potentially surrounded by the raw materials that will become planetary systems. The light you see when you look at the Orion Nebula tonight began its journey to your eyes around the year 680. When that light started traveling toward Earth, the Roman Empire was still centuries away from falling. Vikings hadn't yet begun their age of exploration, and Charlemagne wouldn't be born for another century. You're seeing ancient light from a stellar nursery where stars are being born this very moment. Within nebulae like Orion, the process of star formation continues as it has for billions of years. Gravity slowly pulls together vast clouds of hydrogen and helium, compressing them until nuclear fusion ignites and a new star begins to shine. Around these newborn stars, the leftover material often coalesces into planetary systems. We're witnessing the birth of future solar systems, future worlds that might one day harbor their own forms of life. Our entire galaxy, this vast collection of 200 billion stars, countless planets, magnificent nebulae, and ancient stellar populations spanning 100,000 light-years, represents just one island of matter in a universe that contains structures so large they make our galaxy appear as insignificant as Earth appears when compared to our solar system. The Milky Way, vast as it seems, is merely the first step in understanding our cosmic address. And we're about to discover that it's barely a speck of dust in the true architecture of the universe. Our galaxy doesn't exist in isolation. The closest galaxy to the Milky Way is the Canis Major dwarf galaxy, located only 25,000 light-years from our galactic center. This small, irregular collection of stars is being literally torn apart by the Milky Way's gravitational forces. We're watching galactic cannibalism in slow motion as our galaxy slowly devours its smaller neighbor over millions of years. The process is both violent and beautiful. Streams of stars are being pulled away from the Canis Major dwarf, creating flowing ribbons of light that spiral into our galaxy's disk. These stellar streams represent the death of one galaxy and the feeding of another, a cosmic cycle that has been playing out for billions of years across the universe. The gravitational tidal forces stretch and distort the smaller galaxy, gradually stripping away its outer layers of stars until nothing remains but a scattered trail of stellar debris marking where a galaxy once existed. But for a truly spectacular neighbor, we need to look much farther out. The Andromeda Galaxy, also known as M31, sits approximately 2.5 million light-years from Earth. This is our nearest major galactic neighbor, a massive spiral galaxy that contains roughly 1 trillion stars, about 2.5 times more than our own Milky Way. 1 trillion stars. Let that number settle in your mind for a moment. If you could count 1 star per second without stopping, it would take you over 31,000 years to count all the stars in Andromeda alone. 31 millennia of counting just to catalog the stellar population of a single galaxy. This massive stellar city spans approximately 220,000 light-years in diameter, more than twice the size of our own galaxy. The sheer scale of Andromeda becomes even more astounding when you consider what those trillion stars represent. Each one is a nuclear furnace, many larger and more luminous than our Sun. Many are surrounded by their own planetary systems. The number of worlds orbiting stars in Andromeda could easily exceed 1 trillion planets. Imagine 1 trillion Earths, each potentially harboring its own unique story of geological evolution, perhaps even life itself. If Andromeda were bright enough to see its full extent with your naked eye, it would appear 6 times larger than the full moon in our night sky. Instead of the small, fuzzy patch of light visible only in dark skies to dedicated stargazers, Andromeda would dominate the heavens, stretching across a significant portion of the celestial dome. The night sky would be dramatically different, with this enormous spiral galaxy visible as a magnificent cosmic landmark that would have profoundly influenced human culture and mythology throughout history. The light you would see from Andromeda tonight began its journey 2.5 million years ago. When that photon of light started traveling toward Earth, early human ancestors were just beginning to master the use of fire. No cities existed, no written language, no agriculture. The light crossing space toward us predates everything we consider human civilization by an enormous margin. That light has been traveling through the vacuum of space since before the genus Homo even existed. Think about the journey that light has made. For 2.5 million years, it raced through the emptiness between galaxies at 300,000 kilometers per second, never slowing, never stopping, carrying information about a distant spiral galaxy across an almost incomprehensible void. During that journey, ice ages came and went on Earth, continents drifted, species evolved and went extinct, and our entire human lineage emerged from earlier hominids. Andromeda is approaching us at a speed of 110 kilometers per second. This might sound alarming, but given the vast distances involved, this cosmic collision will unfold over an almost unimaginable timescale in approximately 5 billion years. Andromeda and the Milky Way will merge into a single, massive elliptical galaxy that astronomers have playfully nicknamed Milkomeda. During this galactic collision, something remarkable and counterintuitive will happen. Despite the violent-sounding nature of two entire galaxies crashing into each other, virtually no individual stars will actually collide. The spaces between stars are so immense that the stellar populations will mostly pass through each other like two clouds of fireflies merging in the night. The gravitational forces will reshape both galaxies dramatically, triggering massive bursts of star formation as gas clouds collide and compress. But the stars themselves will find new orbits in the combined system. By the time this collision occurs, our Sun will likely have evolved into a red giant and then a white dwarf. Earth, if it still exists, will be a cold, dead world orbiting a stellar remnant. Yet the merger will create one of the largest galaxies in our cosmic neighborhood, a testament to the dynamic nature of the universe, even on the grandest scales. The Milky Way, Andromeda, and approximately 54 smaller galaxies together form what astronomers call the local group. This gravitationally bound family of galaxies extends roughly 10 million light-years in diameter. To put this in perspective, remember that our entire galaxy spans 100,000 light-years. The local group is 100 times larger than our galaxy, representing the next level up in the cosmic hierarchy. Within the local group, each galaxy follows its own orbital path around the common center of mass, dominated primarily by the gravitational influence of the Milky Way and Andromeda. These two massive spirals are like binary stars, circling around each other on a collision course that will take billions of years to complete. The smaller galaxies are caught in this gravitational dance, some orbiting one of the major galaxies, others following more complex paths through the group. The third largest member of our local group is the Triangulum Galaxy, located about 3 million light-years away. This spiral galaxy contains approximately 40 billion stars, significantly smaller than either the Milky Way or Andromeda, but still an enormous stellar city by any reasonable measure. The Triangulum Galaxy will likely be absorbed by the Andromeda-Milky Way merger, adding its stellar population to the future Milky system. Its fate demonstrates how even galaxies, with tens of billions of stars, can become mere footnotes in cosmic evolution. Much closer to home, visible to observers in the southern hemisphere, are the large and small Magellanic Clouds. These irregular dwarf galaxies orbit our Milky Way like cosmic satellites, connected to our galaxy by streams of hydrogen gas stripped away by tidal forces. The large Magellanic Cloud contains about 30 billion stars and lies 163,000 light-years away, while the small Magellanic Cloud sits at roughly 200,000 light-years distance. The Magellanic Clouds have been faithful companions to our galaxy for billions of years, but their loyalty comes at a cost. Both galaxies are slowly being consumed by our galaxy's gravitational appetite. Over the next few billion years, they will gradually spiral inward and eventually be absorbed by the Milky Way. We're witnessing the slow-motion consumption of these smaller stellar systems, another example of how galaxies grow by consuming their neighbors over cosmic time. As we expand our view beyond the local group, we begin to encounter other galactic neighborhoods scattered throughout space. The M81 group, located about 12 million light-years away, contains 34 galaxies bound together by gravity. At the center of this group lies M81, a magnificent spiral galaxy similar to our own, surrounded by various dwarf companions and irregular galaxies. The Sculptor group sits at approximately 13 million light-years and hosts several bright spiral galaxies, each containing billions of stars arranged in elegant spiral patterns. The Canes Venatici Wine group, the M101 group, the NGC 672 group, Each represents a gravitationally bound family of galaxies, each containing dozens of stellar cities, each hosting billions upon billions of stars. The names become a litany of cosmic architecture, marking the locations of galactic neighborhoods scattered across hundreds of millions of cubic light-years of space. The farther we look from our local group, the more individual galaxies begin to lose their distinctiveness. At these vast distances, galaxies start to merge into statistical distributions, becoming data points in the cosmic census rather than individual objects with unique characteristics and histories. A galaxy like the Milky Way, which seems so vast and significant from our perspective, begins to lose its special status in the face of such overwhelming abundance. Within a radius of 100 million light-years from our local group, astronomers have cataloged approximately 500 similar galaxy groups. 500 separate galactic families, each containing dozens of galaxies, each galaxy containing billions of stars, each star potentially surrounded by its own family of planets. The numbers become so vast, they lose all connection to human experience. We're looking at perhaps 50,000 galaxies within this relatively local region of space. The cosmic hierarchy begins to reveal itself with crystalline clarity. Planets orbit stars. Stars form galaxies. Galaxies cluster into groups, and groups themselves are organized into even larger structures that we're only beginning to understand. Each level up in this hierarchy makes the previous level seem insignificant by comparison. What seemed vast at one scale becomes a mere component at the next. To visualize this scale, if the entire Milky Way were reduced to a grain of rice sitting on a table, the local group would be roughly the size of a large room. And within that room-sized local group, our rice-grain galaxy would contain every star visible in the night sky, every constellation you've ever seen, every nebula astronomers have photographed, every place humans have ever been or could ever hope to visit in the lifetime of our species. At this scale, Earth becomes something beyond tiny. It would be billions of times smaller than an individual atom, completely lost in the immense scope we're now contemplating. Any observer in a distant galaxy within the local group wouldn't be able to detect Earth even with telescopes far more advanced than anything we can imagine. Our entire planet would be far below the resolution limit of any conceivable technology. We wouldn't just be invisible, we would be theoretically undetectable. Even our entire galaxy would appear as nothing more than a faint point of light among billions of other similar points scattered throughout space. The Milky Way, with all its magnificent spiral structure, its stellar nurseries where new stars are born, its ancient populations of red giant stars, its complex gravitational dynamics, would be reduced to a single pixel in any image taken from the distance of neighboring galaxy groups. All the complexity and beauty and history of our galactic home compressed into a dot of light, indistinguishable from countless others. This is where we begin to understand that Earth isn't merely small in the cosmic sense. It's below the detection threshold of the universe itself. We exist at a level of scale so minute that we effectively don't register in any cosmic accounting. Yet, here we are, contemplating scales that dwarf our comprehension, and somehow finding meaning in our investigation of this vast tapestry of matter and energy. And we're only just beginning to grasp how deep this hierarchy of scale actually goes. Our local group, vast as it seems with its 10 million light-year span and its collection of dozens of galaxies, is actually just a peripheral member of something much, much larger. We belong to the Virgo supercluster, a gravitational structure that dwarfs our galactic neighborhood the way our galaxy dwarfs our solar system. The Virgo supercluster contains at least 100 galaxy groups and clusters scattered across approximately 110 million light-years of space. That's 11 times larger than our local group. Imagine taking our entire galactic family and placing it within a structure 11 times more vast, populated by hundreds of other galactic families, each containing dozens of galaxies, each galaxy hosting billions of stars. At the gravitational heart of this supercluster lies the Virgo cluster itself, located about 54 million light-years from Earth. This central hub contains approximately 1,500 galaxies concentrated in a relatively small region of cosmic space. 1,500 entire galaxies, each one comparable to our Milky Way in scale and stellar population, all bound together in a single massive cluster that serves as the gravitational anchor for our entire cosmic neighborhood. If we could somehow position ourselves far outside the Virgo supercluster and look back at our cosmic home, it would appear as a gigantic cloud of luminous points floating together in the darkness. Each point of light would represent not a single star, but an entire galaxy containing hundreds of billions of stars. The supercluster would look like a three-dimensional constellation of galaxies, a stellar city of unimaginable proportions, suspended in the cosmic dark. But recent astronomical discoveries have revealed that even the Virgo supercluster is just a component of something larger still. Our supercluster is actually part of an even more massive structure called Laniakea, a name that means immeasurable heaven in Hawaiian. How perfectly fitting for a structure that truly defies human comprehension. Laniakea extends approximately 520 million light-years across and contains roughly 100,000 galaxies gravitationally connected to each other. 100,000 galaxies. If each galaxy contains an average of 100 billion stars, we're looking at 10 quadrillion stars within this single cosmic structure. That's a number with 16 zeros. If you could count one star per second, it would take you over 300 million years to count all the stars in Laniakea. Our local group sits on the outer edges of Laniakea, far from its dense gravitational center, known as the Great Attractor. This region pulls thousands of galaxies, including our own Milky Way, toward it with inexorable gravitational force. Despite its dramatic name, the Great Attractor is simply a region where matter has accumulated in unusually high density. Dark matter, galaxies, and gas, all concentrated together to create a gravitational anomaly that influences the motion of galaxies across hundreds of millions of light years. We're actually falling toward the Great Attractor right now, along with our entire local group. Our galaxy, moving at over 600 kilometers per second relative to the cosmic microwave background, is being drawn along with countless other galaxies in a vast cosmic migration toward this gravitational beacon. It's a journey that will take billions of years to complete, but it demonstrates that even structures as vast as galaxy superclusters are dynamic, evolving systems rather than static cosmic architecture. Beyond Laniakea stretch other superclusters of similar scale and grandeur. The Shapley supercluster lies about 650 million light-years away and contains more than 8,000 galaxies densely packed together. The Horologium Reticulum supercluster, the Hydra Centaurus supercluster, each represents a collection of tens of thousands of galaxies, each galaxy containing billions of stars, each star potentially surrounded by planetary systems. At this scale, individual galaxies begin to disappear as distinct entities and become merely statistical data points in the distribution of matter across cosmic space. A galaxy like the Milky Way, with all its spiral arms and stellar nurseries and ancient globular clusters, becomes just one point of light among thousands in a supercluster. The rich complexity and history and beauty of our galactic home gets reduced to a coordinate in a vast cosmic census. Between these superclusters lie cosmic voids, vast regions where very few galaxies are found. The Boötes Void measures approximately 330 million light-years in diameter and contains only about 60 galaxies in its entire volume. If the average density of matter in the universe applied to the Boötes Void, it should contain roughly 2,000 galaxies instead of just 60. It's as if someone scooped out galaxies from this region of space, leaving behind a nearly empty spherical cavern in the cosmic structure. These voids aren't completely empty, though. They contain filaments of dark matter and extremely diffuse gas spread throughout their volumes. The matter is there, but it's distributed so thinly that galaxies rarely form in these regions. It's like comparing the density of air at sea level to the near vacuum of space. Matter exists in both places, but in vastly different concentrations. Together, superclusters and voids form the large-scale structure of the universe, creating what astronomers call the cosmic web. Galaxies concentrate along long filaments and walls that connect superclusters, while vast voids create empty spaces between these structures. The result looks remarkably like a three-dimensional foam or spider web stretching across billions of light-years of space. One of the largest known structures in this cosmic web is the Sloan Great Wall, a filament measuring 1.37 billion light-years in length. This immense chain of galaxies contains tens of thousands of stellar cities aligned like lights on a cosmic Christmas tree stretching across more than 1 billion light-years of space. To put this in perspective, if the Milky Way were the size of a grain of rice, the Sloan Great Wall would be longer than 10 football fields. These massive structures began forming roughly 380,000 years after the Big Bang, when the universe had cooled enough for matter to begin clumping together under the influence of gravity. Tiny quantum fluctuations in the primordial universe, variations in density smaller than atomic nuclei, were amplified by gravitational attraction over billions of years of cosmic evolution. What started as microscopic ripples in the fabric of space-time gradually grew into the largest structures we observe in the universe today. Dark matter played a crucial role in this process, providing the gravitational scaffolding around which normal matter could accumulate to form stars and galaxies. Computer simulations can reproduce the cosmic web using nothing more than gravity and dark matter as primary ingredients, demonstrating how simple physical laws can create structures of breathtaking complexity and beauty over cosmic time. The distribution of matter throughout the universe isn't random. It follows predictable patterns determined by the gravitational evolution of dark matter over billions of years. The cosmic web represents the largest scale organization of matter in the universe, a vast network of connected structures that emerged from the quantum foam of the early universe through the patient work of gravity, acting over unimaginable spans of time. At this scale of cosmic architecture, the position of Earth, or even our entire Milky Way galaxy, becomes statistically irrelevant to the overall structure. We're like a single grain of sand, not on a beach, but scattered somewhere in a desert that covers an entire continent. Our location, our existence, our entire cosmic neighborhood becomes lost in the statistical noise of matter distribution across billions of light years. The cosmic web reveals something profound about the universe. It possesses a hierarchical organization that extends far beyond anything we initially imagined. Atoms form molecules. Molecules form rocks and planets. Planets orbit stars. Stars form galaxies. Galaxies cluster into groups. Groups form superclusters. Superclusters connect into filaments and walls, and these filaments weave together the largest scale structure of the observable universe. Each level up in this hierarchy makes the previous level seem not just small, but insignificant. What appears vast and important at one scale becomes merely a component at the next. The cosmic web shows us that structure and organization exist at every scale we can observe, from the smallest quantum fluctuations to the largest galactic superclusters, all connected by the same physical laws that govern matter and energy throughout the universe. We're beginning to see that our cosmic address isn't just Earth, solar system, Milky Way galaxy. It's Earth, solar system, Milky Way galaxy, local group, Virgo supercluster, Laniakea supercluster, positioned on a filament of the cosmic web that connects structures across billions of light-years of space. And even this vast address represents only a tiny fraction of what we're about to discover exists beyond our current ability to observe. We've been building our cosmic address piece by piece, expanding our perspective from Earth to the solar system, to the galaxy, to galaxy groups and superclusters. But now we need to step back and consider the ultimate boundary of what we can possibly know about the universe. We're about to explore the observable universe itself and discover that even this seemingly ultimate scale may be just the beginning. The observable universe is defined as the region of space from which light has had enough time to reach us since the beginning of everything. The universe is approximately 13.8 billion years old, dating back to the Big Bang, when all matter and energy came into existence in an incomprehensible burst of creation. You might think this means the observable universe extends 13.8 billion light-years in every direction, but the expansion of space changes everything dramatically. Due to the accelerating expansion of space itself, the observable universe currently has a radius of approximately 46.5 billion light-years in all directions. This means the complete observable universe spans about 93 billion light-years in diameter, a sphere centered on Earth that represents the totality of everything we can possibly observe, detect, or study. The volume of this observable sphere equals roughly 4 times 10 to the 80th power cubic meters. That's a number so vast it defies any attempt at visualization. 4 followed by 80 zeros. To put this in perspective, if you wrote out this number with each digit the size of an atom, the number itself would be larger than the observable universe can contain. Here's something that might shift your perspective even further. Every location in the universe has its own observable sphere of exactly the same size. A hypothetical observer on a planet 50 billion light-years away would see their own 93 billion light-year sphere of observable space. Some of what they observe would overlap with what we can see, but much of their observable universe would be completely beyond our cosmic horizon, forever invisible to us, no matter how long we wait or how advanced our technology becomes. Within our observable universe, conservative estimates suggest there are between 100 billion and 200 billion galaxies. But more recent studies using data from the Hubble Space Telescope have increased this estimate dramatically, suggesting approximately 2 trillion galaxies exist within our cosmic sphere. However, analyses based on measurements of the darkness of the night sky suggest the number might be somewhat lower, perhaps closer to 200 billion. Let's work with a middle estimate. Assuming an average of 200 billion stars per galaxy, we arrive at roughly 10 to the 24th power stars in the observable universe. That's 1, followed by 24 zeros. This number is larger than all the grains of sand on all the beaches of Earth combined. If you could count 1 star per second without stopping, it would take you 10 to the 16th years to count them all. That's millions of times longer than the current age of the entire universe. For every star you can see in the night sky with your naked eye, perhaps 3,000 stars on a perfectly dark night. There are roughly 100 billion stars invisible to human sight. The night sky you see represents an infinitesimally small fraction of the stars that actually exist. Most of the universe remains hidden from direct human perception, accessible only through our most sophisticated telescopes and instruments. The most distant galaxy we've ever observed lies approximately 4 billion light-years away, near the very edge of what we can possibly see. The light from this ancient galaxy was emitted only 400 million years after the Big Bang, when the universe was young, hot, and dramatically different from today. We're seeing this galaxy not as it is now, but as it was in the cosmic dawn, when the first generation of stars was still forming. When you observe distant objects in space, you're literally looking into the past. The light from these faraway places has been traveling toward you for billions of years, carrying information about conditions that existed long before Earth even formed. Astronomy is fundamentally a time machine, allowing us to observe the history of cosmic evolution written in the light from distant stars and galaxies. The oldest light we can detect is the cosmic microwave background radiation, emitted approximately 380,000 years after the Big Bang. This ancient glow comes from all directions in space and marks the absolute limit of what we can observe using conventional electromagnetic radiation. Before this time, the universe was opaque to light, filled with a hot plasma that scattered photons and prevented them from traveling freely through space. Beyond this cosmic horizon lies what we might call a cosmic event horizon, a boundary we can never cross or observe directly, no matter what technology we develop or how long we wait. There's more universe out there, almost certainly, but it's forever beyond our ability to study. It's like standing at the edge of an infinite ocean and realizing that no matter how far you can see, there's always more water beyond the horizon. The accelerating expansion of the universe creates another profound limitation. Galaxies beyond a certain distance are receding from us faster than the speed of light due to the expansion of space itself. This doesn't violate relativity, because it's space itself that's expanding, not the galaxies moving through space. But it means that these distant galaxies will never be reachable, even if we could travel at the speed of light for eternity. In approximately 100 billion years, cosmic expansion will have carried distant galaxies so far away that future civilizations will see only the galaxies in the local group. The night sky of the far future will be almost completely black, with only a handful of nearby galaxies still visible. Future astronomers will have no way to discover that a larger universe exists beyond their small cosmic neighborhood. They'll inhabit a universe that appears to contain only a few dozen galaxies in total. Our observable universe represents only a minute fraction of the total universe, which may be infinite in extent. If the universe is truly infinite, then there exist infinite galaxies, infinite stars, and infinite planets, exactly like Earth somewhere in the vast expanse beyond what we can see. Theories of cosmic inflation suggest that the total universe could be 10 to the 23rd power times larger than the region we can observe. On this incomprehensible scale, our entire observable universe, with its 2 trillion galaxies and countless billions of stars, would be nothing more than a microscopic point in an infinite ocean of space. The 93 billion light-year sphere that represents everything humans can ever hope to study would be like a single atom floating in an endless cosmic sea. To truly grasp this scale, if the entire observable universe were somehow compressed down to the size of Earth, our Milky Way galaxy would shrink to smaller than subatomic particles. Our solar system would be many orders of magnitude smaller than quarks, and Earth would be so far below any measurable scale that it would cease to have any meaningful definition at all. In this context, Earth doesn't merely fail to exist in any significant sense. It exists so far below any scale that matters cosmically that it challenges the very meaning of existence. We live on a world that is smaller than the smallest meaningful unit in the cosmic accounting. We are inhabitants of a place that registers as literally nothing in the grand scheme of universal structure. Yet here's the profound paradox we face. From this impossibly tiny platform, using instruments no larger than buildings, we've managed to map the structure of the observable universe. We've discovered cosmic microwave background radiation, measured the acceleration of cosmic expansion, cataloged billions of galaxies, and traced the history of the universe back to fractions of a second after its birth. We exist at a scale so minute, we're effectively invisible, yet we've become the universe's way of understanding itself. The observable universe, vast beyond all comprehension, may itself be just a grain of sand on an infinite cosmic beach. And we're not even visible on that grain of sand. We exist at a scale so minute we're effectively invisible, yet we've become the universe's way of understanding itself. But to truly understand how insignificant Earth is in the cosmic scheme, we need to examine how modern cosmology actually treats matter and structure in the universe. In cosmological models, individual galaxies are treated like particles in a statistical distribution of matter across space. Just as we don't track individual molecules of gas bouncing around in a room when studying air pressure and temperature, cosmologists don't concern themselves with individual galaxies when modeling the large-scale structure and evolution of the universe. Think about that for a moment. Entire galaxies, each containing hundreds of billions of stars, become nothing more than statistical data points in cosmological equations. Our Milky Way, with all its spiral arms and stellar nurseries and ancient globular clusters, gets reduced to a single point in a vast statistical distribution. And if galaxies themselves are just data points, what does that make Earth? The average density of matter in the universe is approximately 1 atom of hydrogen per cubic meter of space. That sounds incredibly empty, doesn't it? If you could mark off a cubic meter of space anywhere in the universe and count the atoms inside, you would typically find just one lonely hydrogen atom rattling around in that entire volume. Yet, when you multiply this seemingly negligible density by the immense volume of the observable universe, it accounts for all the matter we can detect. But here's where our perspective on reality takes another profound shift. The vast majority of matter in the universe, about 85%, is dark matter, invisible and mysterious. Dark matter doesn't emit, absorb, or reflect light in any way we can detect. It reveals itself only through its gravitational effects on the matter we can see. It's the invisible scaffolding that holds the cosmic web together, the hidden architecture that shapes the distribution of galaxies across billions of light years. Even more mysterious is dark energy, which constitutes approximately 68% of the total energy content of the universe. Dark energy is what's driving the accelerating expansion of space itself, pushing distant galaxies ever farther apart. We can measure its effects, but we have no idea what it actually is. It's the dominant component of reality, yet it remains completely beyond our direct experience. This means that normal matter, the atoms that make up stars, planets, and people, represents only about 5% of everything that exists. Everything you can see, touch, or measure directly is just a tiny fraction of total reality. The entire visible universe, with all its galaxies and stars and cosmic structures, is merely the foam on top of an ocean of invisible matter and energy. Earth, composed entirely of normal matter, represents an even smaller portion of this already insignificant 5%. In terms of mass, our planet represents about 0.03% of the total mass of our solar system, which is dominated overwhelmingly by the Sun. That's 3/10,000ths of 1% of our local cosmic neighborhood. Our solar system itself represents a minuscule fraction of the mass of the Milky Way, estimated at roughly 1.5 trillion solar masses. Most of that galactic mass is dark matter, forming an invisible halo that extends far beyond the visible edge of our galaxy. The Milky Way, in turn, represents just an average galaxy among the roughly 200 billion galaxies in the observable universe. When you calculate these proportions, Earth represents approximately 10 to the negative 58th power of the total mass of the observable universe. That's a decimal point followed by 57 zeros, and then a 1. It's a number so incomprehensibly small that it challenges the limits of mathematical expression. To put this in perspective, the probability of randomly selecting Earth from all the matter in the universe is smaller than finding one specific atom in all the oceans of Earth. Meanwhile, astronomical events of staggering magnitude occur constantly throughout the universe. Approximately 275 million stars are born every day in the observable universe, each one a nuclear furnace that will burn for millions or billions of years. Simultaneously, about 150 million stars die each day, some exploding spectacularly as supernovas that briefly outshine entire galaxies. A typical supernova releases about 10 to the 51st power ergs of energy. That's equivalent to 100 trillion atomic bombs exploding simultaneously. The energy output of a single supernova in 1 second exceeds the total energy output of our Sun over its entire 10 billion-year lifetime. Yet even these colossal explosions are barely noticeable beyond a few million light-years. Local events in the context of galactic structure. When supermassive black holes merge in distant galaxies, they create ripples in the fabric of spacetime itself. Gravitational waves that propagate across billions of light-years. These waves represent distortions in space and time so subtle that detecting them requires instruments capable of measuring changes smaller than 1 per 10,000th the width of a proton. The universe produces events of unimaginable energy that barely register as whispers by the time they reach us. The universe constantly generates phenomena of incredible power and scale that have absolutely no measurable effect on Earth or our solar system. Gamma-ray bursts release more energy in 10 seconds than our Sun will produce in its entire lifetime. Galactic collisions reshape the structure of space across hundreds of thousands of light years. Quasars, powered by supermassive black holes, shine with the luminosity of 1 trillion stars. All of this cosmic violence and beauty unfolds without the slightest impact on our tiny world. Conversely, everything that happens on Earth, every war, every civilization, every mass extinction, every technological breakthrough, doesn't register even a whisper on the cosmic scale. The rise and fall of entire species, the movement of continents, the formation and erosion of mountain ranges, all of human history from the first cave paintings to space exploration. None of it produces any detectable signal beyond our immediate vicinity. If Earth disappeared entirely at this very moment, the universe would continue exactly as before, without any perturbation detectable anywhere. The gravitational influence of our planet extends only a few million kilometers into space before becoming indistinguishable from the background gravitational noise of the solar system. Beyond the Moon's orbit, Earth's gravity becomes lost in the much stronger gravitational fields of the Sun and outer planets. Even our most powerful radio transmissions beaming signals into space for the past century have created only a tiny bubble of artificial radio waves extending roughly 200 light-years from Earth. This represents about 0.0002% of the diameter of the Milky Way, a microscopic droplet in the galactic ocean. Any extraterrestrial civilization more than 200 light-years away would have no idea that Earth hosts an intelligent species capable of communication. A radio bubble expanding at the speed of light represents humanity's entire footprint in the cosmos. Everything we've ever broadcast, television signals, radio communications, radar pulses, exists within this slowly expanding sphere that remains invisible against the vast backdrop of our galaxy. In cosmic terms, we've been shouting into the darkness for a century, but our voices carry only as far as a whisper in the galactic din. For the universe at large-scale structure, Earth doesn't merely fail to exist in any significant sense. It couldn't exist as a measurable entity, even in principle. We operate at a scale so far below the resolution limit of cosmic physics that we exist in a realm of complete statistical irrelevance. We're not just small, we're smaller than the smallest meaningful unit in the cosmic accounting system. Yet the profound paradox remains. From this platform of ultimate cosmic insignificance, we've somehow managed to map the structure of the observable universe, discover dark matter and dark energy, measure the age and expansion rate of the cosmos, and trace the evolution of galaxies across billions of years. We exist at a scale that registers as literally nothing in cosmic terms, yet we've become conscious observers capable of comprehending scales that dwarf our imagination. The universe has produced in us a way of examining itself, of recognizing its own vast scales, and understanding its own evolution. We are the cosmos becoming aware of itself, even though we exist at a level so minute that we're essentially invisible to the very system we're studying. But this brings us to the heart of a deeper question. The central issue isn't exactly that Earth is small, but whether existing has any meaning outside the human context at all. We've been measuring scales and comparing sizes, but perhaps we need to step back and examine what we mean when we say something exists in a meaningful sense. Physical objects exist in a clear hierarchy of scales. Quarks combine to form protons and neutrons. Protons and neutrons form atomic nuclei. Nuclei combine with electrons to form atoms. Atoms bond together to create molecules, and so on, building complexity level by level. At each level in this hierarchy, the properties of the previous level become statistical averages rather than individual characteristics. Consider this carefully. A single carbon atom in your body doesn't possess the properties of you. That carbon atom has no personality, no memories, no hopes or fears. It follows the laws of quantum mechanics and electromagnetic forces, but it knows nothing of love, ambition, or curiosity. The qualities we associate with human consciousness and identity emerge only from the collective organization of trillions of atoms working together in incredibly complex patterns. The individual components have completely different properties than the emergent whole. Your thoughts right now arise from the coordinated firing of billions of neurons. Each neuron is just a biological cell following biochemical processes. No individual neuron contains your memories or experiences. No single cell in your brain holds the concept of beauty or justice or wonder. These emerge only when vast networks of neurons work together in specific patterns. The meaning exists in the organization, not in the individual components. Similarly, an individual galaxy doesn't possess the properties of a supercluster. A galaxy has spiral arms, stellar populations, a central black hole, regions of active star formation, but a supercluster has none of these characteristics. Instead, it has properties that emerge only from the statistical distribution of many galaxies across vast regions of space. Filamentary structure, gravitational flow patterns, large-scale density variations, properties that exist only at the supercluster level and have no meaning when applied to individual galaxies. Earth exists as a physical object, absolutely. You can measure its mass, calculate its orbital parameters, analyze its geological composition, but it doesn't exist as a significant entity in the physics of the universe at large scales. Modern cosmological models treat the universe as a continuous fluid where matter is uniformly distributed when averaged over sufficiently large volumes. In these models, local variations like stars, galaxies, and certainly planets are negligible fluctuations below the resolution threshold used in the analysis. It's like trying to study Earth's global climate while worrying about each individual butterfly flapping its wings in your garden. The butterfly's wing beats are real physical events that displace air molecules and create tiny pressure variations, but they operate at a scale so far below what matters for global weather patterns that including them in climate models would be meaningless. They exist physically, but they don't exist in any way that affects the phenomena being studied. The equations that govern the evolution of the universe at large scales contain no term for Earth or any specific planet. Einstein's field equations of general relativity, which describe how matter and energy curve spacetime, assume the universe is homogeneous and isotropic when viewed at sufficiently large scales. The mathematics of cosmology works with concepts like average density, expansion rate, and curvature parameter, but has no variables for individual worlds. Homogeneous means that the average density of matter is the same everywhere when you calculate it over large enough volumes. Isotropic means that the universe looks the same in all directions when observed from any randomly chosen point. These assumptions, known as the cosmological principle, form the foundation of modern cosmology. They allow us to describe the evolution of the entire universe with relatively simple equations. These assumptions are extraordinarily well confirmed by observations of the cosmic microwave background radiation at scales above 100 million light-years. Above this scale, the universe is smooth as a perfectly polished surface with density variations of less than 1 part in 100,000. Below this scale, the universe is lumpy with galaxies, galaxy clusters, and vast cosmic voids, but above it, all that complexity averages out to perfect uniformity. Earth sits approximately 10 orders of magnitude below the scale where cosmic structure begins to matter in cosmological models. 10 orders of magnitude means 10 billion times smaller. This represents a difference so vast that meaningful comparison becomes impossible. If you could somehow magnify a human being by 10 orders of magnitude, that person would be larger than Pluto's orbit around the Sun. The difference between human scale and cosmic scale is that enormous. From the perspective of universe-scale physics, individual planets are like individual electrons from the perspective of a human observer. You can't locate or track specific electrons in your body. They exist in quantum probability clouds, indistinguishable and interchangeable, following statistical patterns rather than individual trajectories. Similarly, the universe cannot locate or assign special meaning to Earth among the potentially 10 to the 24th power planets that exist throughout cosmic space. The universe doesn't have a mechanism for recognizing individual planets any more than you have a mechanism for recognizing individual electrons. Both exist far below the scale of resolution for the relevant physics. When cosmologists model the universe, they work with density fields and gravitational potentials. Individual planets are like individual molecules in a gas, real, but statistically irrelevant. This is where the anthropic principle becomes relevant. We observe the universe from a special position simply because only special positions allow observers to exist. This doesn't make our position objectively special in any cosmic sense. It's only special to us, beings who require very specific conditions to survive and develop consciousness. The universe is full of places where no observers could exist. We naturally find ourselves in one of the rare places where observation is possible. A thermometer always measures temperatures in environments where thermometers can function. But this doesn't make those temperature ranges cosmically significant. The thermometer's measurements tell us about the conditions where thermometers work, not about the fundamental importance of those temperatures to the universe as a whole. Earth is special to us for exactly the same reason a thermometer only works within certain temperature ranges. Observational selection eliminates all the cases where we couldn't exist to observe. Advanced civilizations on other planets throughout the universe probably engage in precisely the same philosophical debates about their place in the cosmic hierarchy. Each civilization would discover their own version of the cosmic distance ladder. Each would conclude that their home world is cosmically insignificant, while perhaps remaining locally or philosophically meaningful to its inhabitants. Each would discover the same vast scales, the same hierarchies of structure, the same apparent meaninglessness of their individual world in the context of cosmic architecture. Every alien astronomer looking through their telescopes would see the same cosmic web of galaxy filaments and voids. They would discover their own galaxy is one among hundreds of billions. They would realize their star system orbits in the galactic suburbs. They would calculate that their planet represents an infinitesimally small fraction of cosmic mass and energy. They would measure the same cosmic microwave background, the same Hubble constant, the same large-scale structure. They would face exactly the same existential questions about scale and significance that we're exploring. Imagine an alien philosopher on a world orbiting a red dwarf star in the Andromeda galaxy. They would look out at the cosmic web and see their galaxy as part of the same local group we belong to. They would discover that their entire galactic neighborhood is falling toward the same great attractor that influences our motion. They would calculate the same cosmic scales and reach the same conclusions about their own cosmic insignificance. The physics is universal, so the philosophical implications would be universal too. The vastness of the universe doesn't diminish the subjective value of conscious experiences happening on Earth or any other world. A sunset remains beautiful, regardless of how many light years of empty space surround our solar system. Love between two people retains its meaning, whether or not there are trillions of other planets hosting similar relationships. Art, music, literature, scientific discovery all maintain their value independent of cosmic scale. Consider the act of reading these very words. Your brain is processing symbols, extracting meaning, contemplating ideas about cosmic scale and existence. This is a real phenomenon happening in a specific place at a specific time. The fact that it's occurring on an infinitesimally small planet in an unremarkable galaxy doesn't make the experience any less real or valuable to you. The meaning exists in the pattern of neural activity, not in the cosmic coordinates where it happens. Meaning isn't a physical property that can be measured like mass or energy. It's not something that exists in the equations of physics or the structure of space-time. Meaning belongs to an entirely different category of reality, the realm of conscious experience, subjective value, and existential significance. These aren't physical phenomena that can be weighed or detected by instruments. They're emergent properties of complex information processing systems, properties that arise when matter organizes itself in certain extraordinarily specific ways. The universe doesn't need to acknowledge Earth for Earth to serve as the stage for experiences, thoughts, loves, and discoveries. Cosmic indifference doesn't negate human significance any more than your indifference to the quantum mechanics in your coffee cup negates the cup's usefulness for holding your morning drink. Significance operates at the appropriate scale for the phenomena being considered, When you experience joy at hearing your favorite music, that joy is real and meaningful at the scale of human consciousness. The fact that your neural activity represents an infinitesimally small energy fluctuation in the cosmic energy budget doesn't make the experience any less real or valuable. The meaning exists in the pattern, the organization, the information processing, not in the raw matter and energy that make it possible. The universe doesn't need to recognize Earth for Earth to be home to consciousness, creativity, wonder, and the peculiar phenomenon of matter examining itself. We exist at a scale so minute that we register as essentially nothing in cosmic physics, yet we've somehow become the mechanism through which the universe develops self-awareness. Here's one of the most profound peculiarities of existence. The universe has somehow produced structures capable of contemplating their own cosmic insignificance. After 8 billion years of expansion, cooling, and evolution, matter has organized itself in such extraordinarily specific ways that it can now examine its own origins and question its own meaning. Human consciousness represents an extraordinarily unusual form of matter organization capable of modeling and comprehending the cosmos that created it. Approximately 86 billion neurons in your brain create patterns of electrical and chemical activity that you experience as thoughts, emotions, and perceptions. Each individual neuron is simply a biological cell processing information through electrochemical signals, following the same biochemical rules as any other cell. Yet somehow, when billions of these cells work together in precise coordination across complex networks, they generate the phenomenon you call consciousness. The ability to experience, to wonder, to contemplate scales that dwarf comprehension. Those neurons themselves are constructed from atoms that were forged in the nuclear furnaces of stars that exploded billions of years before Earth even existed. The carbon in your DNA, the oxygen you breathe with every breath, the nitrogen in your proteins, the calcium in your bones, the iron flowing through your bloodstream. All these elements were created through nuclear fusion in the cores of massive stars that lived fast, burned bright, and died spectacular deaths long before our solar system even began to form. When these ancient stars exhausted their nuclear fuel and collapsed under their own gravity, they exploded as supernovas, dispersing these newly created elements throughout the surrounding interstellar space. These atomic building blocks drifted through the galaxy for millions of years, mixing with clouds of hydrogen and helium left over from the Big Bang, eventually condensing into the nebula that would become our solar system. The same atoms that once burned in stellar cores 10 billion years ago now form the neural networks that allow you to contemplate this very process. We are literally made of stardust. Reorganized stellar material that has somehow arranged itself into patterns complex enough to think about its own cosmic origins. The calcium atoms in your teeth were forged in supernova explosions when the universe was a fraction of its current age. The iron in your blood was created in the collapsing core of a dying star whose light faded billions of years before the first life appeared on Earth. You are not separate from the cosmos. You are the cosmos examining itself through temporary configurations of ancient stellar material. The probability that any specific atom in your body would eventually become part of a conscious being is astronomically small. Literally trillions upon trillions to 1 against. Each carbon atom in your brain has journeyed through interstellar space, possibly through multiple stellar generations, survived the formation of the solar system, found its way into the complex chemistry of early Earth, and somehow ended up in precisely the right configuration to support conscious thought. The odds of this happening to any given atom approach 0. Yet, given the immense number of atoms in the observable universe and the billions of years of cosmic time available for unlikely events to unfold, improbable occurrences become inevitable somewhere in the vast expanse of space and time. With 10 to the 82nd power atoms in the observable universe and nearly 14 billion years for cosmic evolution to experiment with different arrangements, even events with vanishingly small probabilities become virtually certain to occur multiple times. If there are 10 to the 24th power stars in the observable universe, and even a tiny fraction of them host planets in the habitable zone where liquid water can exist, there could still be billions of worlds capable of supporting life as we understand it. The universe may be vast beyond comprehension, but it's also had an enormous amount of time for complex chemistry to experiment with different arrangements of matter and energy. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate how many technological civilizations might exist in our galaxy alone. It considers factors like the rate of star formation, the fraction of stars with planetary systems, the number of planets per system in the habitable zone, the fraction of those planets where life actually emerges, the fraction where intelligent life evolves, and the fraction that develops detectable technology. Depending on the values you assign to these largely unknown parameters, the estimates range from 0 other civilizations in the Milky Way to millions of them scattered throughout our galactic neighborhood. This leads directly to Fermi's paradox, named after physicist Enrico Fermi, who first articulated the question in 1950. If alien civilizations are reasonably probable based on the sheer number of potentially habitable worlds, where is everybody? Why haven't we detected any signals from extraterrestrial intelligence? Why does the universe seem so eerily quiet when it should be bustling with activity across thousands of different civilizations? Several possibilities might explain this cosmic silence. Perhaps consciousness is far rarer than we imagine, requiring such specific conditions and unlikely coincidences that it occurs only once every few galaxies. The chain of events leading to complex life might involve so many improbable steps that Earth represents a cosmic lottery ticket that almost never wins. Perhaps civilizations tend to destroy themselves shortly after developing advanced technology, creating a great filter that prevents most species from achieving long-term survival. Nuclear weapons, climate change, resource depletion, or some other technological crisis might doom most civilizations before they can establish contact with others. Or perhaps advanced civilizations become so sophisticated that they have no more interest in communicating with primitive species like ourselves than we have in attempting meaningful conversations with ants. They might have transcended the need for electromagnetic communication, or evolved beyond our ability to recognize their activities as the products of intelligence. What we interpret as natural phenomena might actually be the engineering projects of civilizations so advanced that their technology appears indistinguishable from natural processes. Alternatively, the distances between civilizations might be so vast that meaningful contact becomes practically impossible, even with advanced technology. Remember that our nearest stellar neighbor lies 4.24 light-years away. A radio message to Proxima Centauri takes 4.24 years to arrive, and another 4.24 years for any response to return. That's nearly a decade for the simplest possible exchange of hello and hello back. For a civilization 1,000 light-years away, a conversation would require 2,000 years between question and answer. On these time scales, entire civilizations could rise, flourish, and fall before completing a single meaningful exchange of information. Human civilization, as we know it, has existed for only a few thousand years. By the time we receive a response from a distant alien civilization, our entire species might have evolved into something unrecognizable. Perhaps the universe is indeed full of consciousness, but each island of thought remains hopelessly isolated by the sheer vastness of interstellar and intergalactic space. Millions of civilizations might exist throughout the cosmos, each one contemplating the same question we face, each one wondering why they seem to be alone, each one separated from the others by distances so vast that communication becomes meaningless. Or perhaps consciousness is extraordinarily rare. A statistical accident so improbable that it happens only once per galaxy or once per billion galaxies. If that's the case, then each conscious civilization becomes incredibly precious, representing something unique and irreplaceable in the cosmic order. Earth might be cosmically insignificant in terms of mass and energy, but biologically unique as the only known location where complex life has actually evolved and achieved self-awareness. This creates a profound duality that sits at the heart of human existence. We appear to be simultaneously irrelevant to the universe and possibly the only beings capable of understanding it. The universe operated for 13.8 billion years without any known observers, without consciousness to appreciate its beauty or wonder about its mysteries. For most of cosmic history, stars were born and died in spectacular nuclear fires. Galaxies formed and evolved through gravitational interactions. Supernovas exploded in displays of energy that outshine entire stellar populations. And no one was there to witness these cosmic symphonies. Then, in this tiny corner of space, on this infinitesimal speck of dust orbiting an ordinary yellow dwarf star in the suburbs of an unremarkable galaxy, something extraordinary happened. Matter organized itself in such a way that it became capable of understanding matter. The universe developed a way to observe itself, to measure its own properties, to trace its own evolution back to the moment of creation. Through us, the cosmos has become self-aware. Yet, this consciousness appears to be a temporary phenomenon in the vast span of cosmic time. For billions of years in the future, the universe will continue its expansion and evolution, utterly indifferent to the emergence and eventual disappearance of any particular civilization. Stars will continue their cycles of birth and death according to the laws of stellar physics. Galaxies will continue their cosmic dance of collision and merger. The large-scale structure of space-time will continue evolving according to the same physical laws that govern everything from quantum particles to cosmic superclusters. There appears to be no cosmic purpose built into the universe, no grand design that requires conscious observers, no ultimate goal toward which everything is progressing. The universe operates through natural laws, not intentions. Purpose is something that conscious beings create for themselves locally within their own brief spans of existence. The absence of cosmic meaning doesn't demand nihilism or despair. Instead, it provides the freedom to create meaning through experiences, relationships, discoveries, and the simple act of conscious appreciation. The universe doesn't care whether we find meaning in our lives, but that doesn't prevent us from creating meaning anyway. A Bach symphony doesn't become less beautiful because it occurs in a galaxy that's cosmically insignificant. Love doesn't become less powerful because it happens on a planet that barely registers in the cosmic census. Scientific discovery doesn't lose its wonder because it takes place in a civilization that will eventually be forgotten by cosmic history. We exist in a universe vast beyond comprehension, operating on scales that make our existence statistically irrelevant. Yet here we are, contemplating these very scales, finding beauty in the cosmic architecture, creating art and music and literature inspired by our place in the grand scheme. Perhaps this is consciousness's role in the cosmos, not to be significant in terms of mass or energy or gravitational influence, but to serve as the universe's way of experiencing wonder at its own existence. The fact that unconscious matter has somehow arranged itself into patterns capable of consciousness, capable of awe, capable of scientific understanding and artistic expression, might be the most remarkable phenomenon in the known universe. We represent an extraordinary experiment in cosmic self-awareness conducted on an infinitesimal scale, but with implications that transcend any measurement of size or significance. Perhaps the final insight is this: cosmic insignificance and personal significance aren't contradictory but complementary aspects of the conscious experience. We began this journey standing on the surface of Earth where everything seemed solid, large, and permanent beneath our feet. The ground felt infinite, stretching endlessly to the horizon. Buildings and mountains appeared massive and immovable. The world felt like the center of everything that mattered. We started with the illusion that our planet was not just large, but fundamentally important in some cosmic sense. We progressively expanded our perspective until we reached the solar system, revealing that Earth is merely a small point of light, orbiting a much larger, more massive star. Our entire world became a grain of sand next to a basketball. Everything that had seemed vast and significant suddenly appeared tiny and peripheral. Yet even this dramatic shift in scale was only the beginning. We expanded further to encompass the Milky Way, where our entire solar system transformed into a mote of dust in the galactic suburbs, far from the dense, energetic center where most of the action takes place. Our local cosmic neighborhood, which had seemed so important just moments before, became lost among 200 billion other star systems, scattered across 100,000 light-years of space. We traversed the local group of galaxies, then supercluster after supercluster, until we reached the scale of the entire observable universe. At each stage of this expansion, objects that had seemed profoundly significant in the previous context became statistically irrelevant at the next, larger scale. The pattern repeated itself with mathematical precision. What appeared vast at one level became infinitesimal at the next. Earth isn't simply small in some relative sense. It exists below the resolution threshold of any useful cosmological model. If the universe were a textbook of physics describing the fundamental forces and large-scale evolution of cosmic structure, Earth wouldn't merit even a footnote in the equations. Our planet operates at a scale so far below what matters for cosmic physics that including it in universal models would be like trying to predict global climate while accounting for individual butterfly wing beats. This conclusion might initially seem depressing or nihilistic. The natural human reaction to confronting such scales is often despair or a sense of cosmic meaninglessness. If we're so utterly insignificant in the grand scheme of things, why does anything we do matter? But there's an equally valid alternative perspective that deserves serious consideration. The scale of the universe doesn't determine the importance of experiences that happen within it at specific locations like Earth. A Beethoven symphony doesn't lose its beauty or emotional power because it's performed in a small concert hall rather than a massive stadium. The music remains equally moving whether it occurs in a room that seats 100 people or 100,000. The value lies in the complexity, the artistry, the emotional resonance, not in the size of the venue. Love, beauty, creativity, and discovery remain precious regardless of how many light years of empty space surround them. When you experience joy at seeing a sunset, that experience is real and meaningful at the scale of human consciousness. The fact that it's happening on a cosmically insignificant planet doesn't diminish its value to you. The meaning exists in the pattern of neural activity, in the subjective experience of beauty and wonder. The fact that the universe has produced something capable of comprehending its own nature is remarkable, even if that something appears impossibly small from a cosmic perspective. Consciousness represents an extraordinary form of organization that allows matter to examine itself, to ask questions about its own origins and destiny. We don't need to be large to be significant. We only need to be capable of experiencing, questioning, and creating meaning. The vastness of the universe doesn't diminish us. Instead, it places us in context and reminds us of our deep connection to cosmic processes that stretch back billions of years. Every atom in your body has an extraordinary history. The calcium in your bones was forged in the nuclear furnace of a supernova. The iron in your blood was created in the collapsing core of a massive star. The oxygen you're breathing right now was manufactured through stellar fusion billions of years ago. You are literally a way for the universe to know itself, a temporary configuration of ancient stellar material that has somehow become capable of contemplating its own cosmic origins. Carl Sagan captured this beautifully when he said we are made of star stuff. And this isn't poetry or metaphor. It's literally true according to our understanding of stellar nucleosynthesis and the chemical evolution of the cosmos. Earth may not exist at the scale of universal physics, but for us it represents everything, the only known home for life in a cosmos that appears largely empty and sterile. This apparent fragility makes our planet more precious, not less. It highlights our responsibility to preserve this extraordinary oasis of complexity and consciousness in what might otherwise be an unconscious universe. We have no backup planets within reasonable reach, no other worlds that could serve as home for human civilization or the millions of species that share Earth with us. This small world, cosmically insignificant though it may be, remains irreplaceable from our perspective. Every sunset, every forest, every ocean, every ecosystem represents something unique and irreplaceable in our cosmic neighborhood. Human consciousness has allowed the universe to develop a portion of itself dedicated to contemplation and self-aware understanding. For 13.8 billion years, the universe existed without witnesses, without anyone to appreciate its grandeur or puzzle over its mysteries. Stars were born and died in magnificent displays of nuclear fire. Galaxies danced through space in gravitational ballets. Supernovas painted the cosmos with newly created elements, and no one was there to witness these cosmic symphonies. Now, at least in this remote corner of space, there are observers asking questions, building telescopes, developing theories, and attempting to understand the whole magnificent structure. Even though we may be cosmically insignificant in terms of mass and energy, we represent something profoundly significant from the perspective of the universe's emerging consciousness of itself. The cosmic scale teaches us humility. Our daily problems and concerns, which can feel overwhelming and all-consuming, appear minuscule against the backdrop of cosmic space and time. The argument you had yesterday, the deadlines causing you stress, the social dramas that occupy so much mental energy, all of these exist at such a local scale that they barely register as whispers in the cosmic conversation. Yet simultaneously, cosmic scale teaches us courage. Despite being incredibly small, we've managed to map galaxies billions of light years away through persistent scientific investigation. We've traced the history of the universe back to fractions of a second after its birth. We've discovered dark matter and dark energy. We've detected gravitational waves from colliding black holes. From our tiny platform, we've achieved an understanding of cosmic structure that would have seemed impossible just generations ago. Earth essentially doesn't exist in the universe from a physics perspective, but we exist on Earth, and that existence contains everything we know as reality. All of human experience, all of art and science and love and wonder happens here in this cosmically irrelevant location. Perhaps meaning doesn't reside in scale but in complexity. Not in size, but in the capacity to experience and create. The universe remains utterly indifferent to our presence. It will continue its expansion and evolution with complete disregard for human hopes, dreams, or survival. Galaxies will merge, stars will die, new worlds will form, all according to physical laws that operate without consciousness or intention. Yet this cosmic indifference doesn't prevent us from being passionately committed to our existence and to each other. We can choose to find beauty in a flower despite the fact that the flower exists on a planet that barely registers in cosmic accounting. We can create art that moves us deeply, even though that art will never influence the motion of distant galaxies. We can love each other profoundly, regardless of whether that love has any significance beyond our local experience. Cosmic indifference doesn't negate human significance. It simply operates at a different scale. In the end, the cosmic insignificance of Earth isn't a tragedy or cause for despair. It's a liberating truth that frees us to construct meaning on our own terms. We don't need the universe's permission to find our lives meaningful. We don't require cosmic validation to pursue beauty, truth, love, and understanding. The universe may not care about our existence, but we can care deeply about it ourselves. The scales we've explored tonight reveal that we exist in a cosmos of almost incomprehensible vastness and apparent indifference. Yet somehow, in this tiny corner of an unremarkable galaxy, matter has organized itself in such a way that it can contemplate its own cosmic context. We are the universe becoming conscious of itself, even if only briefly and locally, and perhaps that's enough. If you're still awake, it's because the content was really good. So, take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.